Gravitational instability stands as a fundamental mechanism driving the formation of stars across the universe, representing one of the most crucial processes governing the evolution of galaxies and stellar populations. This comprehensive exploration delves into the complex dynamics of gravitational instability in star-forming regions, examining its theoretical foundations, observational evidence, and broader implications for cosmic structure formation. Gravitational instability emerges from the fundamental tension between gravity's inward pull and opposing forces within interstellar gas. The process of gravitational collapse represents the contraction of astronomical objects due to the influence of their own gravity, which inexorably draws matter inward toward the center of gravity. This mechanism serves as the foundation for structure formation throughout the universe, transforming initially smooth distributions of matter into the complex assemblage of stars, clusters, and galaxies we observe today. When examining star formation specifically, gravitational instability follows well-established physical principles that determine when a gas cloud will remain stable versus when it will collapse to form stars. An interstellar cloud maintains hydrostatic equilibrium only when the kinetic energy of gas pressure successfully balances the potential energy of internal gravitational forces. This delicate balance is mathematically expressed through the virial theorem, which stipulates that to maintain equilibrium, the gravitational potential energy must equal twice the internal thermal energy. When a pocket of gas exceeds a critical mass threshold, where internal pressure proves insufficient for support, the cloud inevitably undergoes gravitational collapse. This critical threshold, known as the Jeans mass, represents the tipping point between stability and instability, typically ranging from thousands to tens of thousands of solar masses depending on cloud temperature and density. In rotating systems like galactic disks, gravitational stability becomes significantly more complex, requiring additional considerations beyond simple pressure-gravity balance. Toomey's stability criterion provides a critical framework for understanding when differentially rotating, gaseous accretion disks will remain stable versus when they will fragment. This criterion accounts for the stabilizing effect of rotational shear forces, which supplement thermal pressure in resisting gravitational collapse. The Toomey Q parameter, defined as Q wash, CS, K, PGS for gaseous disks, incorporates sound speed, CS, epicyclic frequency, K, and surface density, S. When Q exceeds 1, the disk theoretically maintains stability against gravitational collapse. However, recent three-dimensional analyses have revealed that even disks classified as Toomey stable, Q1, can experience gravitational instability and structure formation. This occurs because stability varies with height above the galactic midplane. Near the midplane, instability displays Jeans-like characteristics, occurring on scales larger than the Jeans length. This insight helps explain why molecular gas disks that appear generally Toomey stable still exhibit significant cloud formation and star formation activity. Observational studies have definitively established connections between gravitational instability and star formation across diverse galactic environments. In NGC 628, detailed analysis of two-component gravitational instability models demonstrates strong correlation with observed star formation patterns. The relationship proves particularly robust when using a threshold of Kepler 2-3 throughout the studied regions. Compelling differences emerge when comparing gravitational instability processes between galaxy types. Spiral galaxies exhibit higher median star formation rates, lower stability parameters, reduced gas fractions, and shorter timescales for the growth of gravitational instabilities compared to irregular galaxies. This indicates that gravitational instabilities in spiral systems rapidly convert substantial gas reserves into stars, progressively depleting available gas. Conversely, irregular galaxies like the Large and Small Magellanic Clouds demonstrate more gradual, prolonged star formation extending over longer timescales, explaining their characteristically higher gas fractions. These differential patterns raise important questions regarding dark matter's role in regulating both star formation processes and the development of gravitational instabilities across galactic structures. Recent theoretical advances have expanded our understanding of gravitational instability beyond traditional two-dimensional models. Three-dimensional analyses reveal that gas disks can fragment through partial 3D instability even in regions where complete 2D instability appears suppressed. This perspective helps explain the rich structural complexity observed in molecular disks at scales of tens of parsecs. Near the galactic midplane, where equilibrium density remains roughly constant, instability manifests Jeans-like qualities, occurring on scales exceeding the Jeans length and subject to a threshold approximately equivalent to a Tumri Q value around 2. Conversely, regions far from the midplane demonstrate pervasive stability, with the threshold for total disk stabilization reduced to the classical Tumri criterion of Q-1. The growth rates of fragments formed through three-dimensional instability compare favorably with, and sometimes exceed, those of traditional Tumri instabilities. This conceptual framework explains how molecular gas structures develop naturally from the three-dimensional character of galactic disks and their exposure to various vertical perturbations acting approximately at disk scale height. Gravitational instability dynamics become further complicated by the presence of existing stellar populations. When stars populate a region, gravitational instability in the interstellar medium receives significant augmentation from stellar gravitational contributions. The two-fluid swing-amplified instability, involving interactions between both gas and stars, appears common throughout galaxies, manifesting as multiple spiral arms that often exhibit long, irregular patterns in outer galactic regions, while forming more symmetric two-arm structures in inner disk sections. Beyond direct gravitational effects, stellar populations influence subsequent star formation through energetic feedback mechanisms. After initial starbursts, massive stars photoionize the surrounding interstellar medium, creating HII regions that expand outward. The expansion of these HII regions and larger superbubbles can trigger additional star formation in adjacent regions, potentially establishing sequential patterns of star formation across galactic disks. The Large Magellanic Cloud provides compelling evidence for both spontaneous star formation driven by gravitational instability and triggered star formation initiated by stellar feedback processes. Gravitational instability in star-forming regions represents a fundamental process that bridges microscopic gas physics with macroscopic galactic evolution. The delicate balance between gravitational attraction and opposing forces, whether thermal pressure, turbulent motions, or rotational shear, determines where and when new stars will form throughout the universe. Understanding these processes not only illuminates the mechanisms of star formation, but also provides crucial insights into galaxy evolution, cosmic structure formation, and the complex relationship between dark matter, gas dynamics, and stellar populations. As observational capabilities and theoretical models continue advancing, our comprehension of gravitational instability will undoubtedly deepen, revealing further complexities in the cosmic processes that transform interstellar gas into the brilliant tapestry of stars illuminating our universe.